Let the games begin. Yeah, the Hunger Games.
This kite surfer is hitching a ride on a moving air mass. Our transparent atmosphere reveals itself when it starts to move. Moving air, of course, is wind. The atmosphere surrounding us is a deep ocean of air extending for kilometers above us. We know that the atmosphere is essential to life on Earth. The components of air, particularly oxygen and carbon dioxide, play a critical role in the chemistry of life. Another important aspect of air is atmospheric pressure. We live at the bottom of an ocean of air. Gravity pulls on this massive layer of gas, creating pressure. The pressure is greatest at the bottom, the Earth's surface, the level where we live. Pressure is a force per unit area. The standard SI unit of pressure is the Pascal. 1 Pascal is 1 Newton of force per square meter. You will also find PSI, or pounds per square inch, used in parts of the world, particularly America. Air pressure at sea level is 14.7 psi, or 101.3 kilopascals. That's over 101,000 newtons of force per square meter. If you have a small kitchen table, 1 meter square, the force on that area created by air pressure is approximately 101,000 newtons, equivalent to the weight of 10 cars sitting on the tabletop. If air pressure can generate such huge forces, why don't we notice it? Why doesn't the table collapse? It turns out that pressure in a fluid like air transmits in all directions, not just down. This means that the 101,000 newtons of force pushing down on the tabletop is balanced by 101,000 newtons pushing up. Forces are balanced. Similarly, our bodies are not crushed because the fluids contained within our skin exert a pressure that balances atmospheric pressure. Here is a simple demonstration that reveals the presence of atmospheric pressure. Fill a glass with water. Cut a small piece of card large enough to cover the top of the glass. Lay the card on the glass. Hold the card in place and rotate the glass full of water. Surprisingly, the water stays in the glass. Here's the explanation. The card provides a rigid membrane between the water and the air in the room. Air pressure pushes up on the card. Air pressure is not pushing down on the water because there is a vacuum at the top of the water. Air pressure is pushing on the outside of the glass, but this does not affect the water. The only downward force from the water is its weight. The upward force of air pressure easily supports the weight of the water. If we drilled a hole in the top of the glass, air pressure would push on the top of the water would fall from the glass. The forces involved in our above demonstration are impressive. The glass I used in this demonstration has a diameter of 6 centimeters at the open end. The force acting on that small area is an incredible 286 newtons, or 64 pounds. Easily enough force to support the water in the glass. To confirm my numbers, calculate the area of the open end of the glass, then multiply by atmospheric pressure. Interestingly, we couldn't live without atmospheric pressure. In the few minutes you have spent watching this video, your body has been quietly using air pressure to move air in and out of your lungs. The diaphragm, a muscular membrane below your lungs, alternately contracts and relaxes, changing the volume of the body cavity, which changes internal pressure. Low pressure allows air at atmospheric pressure to move down the trachea into the lungs. High pressure forces it out. Without atmospheric pressure, we could not breathe.
How you guys are feeling your breathing right now?
Atmospheric pressure also plays a role in the function of many devices, including water pumps, syringes, and drinking straws. When you use a drinking straw, you're not sucking liquid up the tube. Air pressure pushes the liquid up the tube. For more videos about our atmosphere and other science topics, visit hylaroad.com. Follow the videos link.
Okay, so the big thing is that atmospheric pressure is everywhere. It's putting all kinds of pressure all over our bodies, all over everything in the entire Earth. Our atmosphere is about 300 miles high. Okay, so you got 300, yeah, I looked at it too, I'm like, really? That's the outer atmosphere. Probably about 10 or 15 is really what we live, that kind of area. But yeah, I did some research today. I'm like, how much atmosphere do we really have? But anyway, we have all that weight of the air, water vapor, all those atoms sitting on top of us. Okay? And I like the fact it says, there's no such thing as suction. There's not. Suction's just a word we use to for something, an occurrence. Atmospheric pressure is at work in all that kind of stuff. Like when you breathe, and we'll talk about that a little bit later on. Breathing is a big part of atmospheric pressure. Okay, so I'm going to move my little man back here. I can't remember, we named him something. I can't remember what it was. Okay. So, first thing, the mat. Yes. Guys.
I know with kind of be like in space, we run out of oxygen. What would happen to like a planet or a moon with no pressure? Would it just float away?
Well, no. Actually, atmospheric pressure is just what comes down on the planet. So it's not gravity. The only reason planets don't float away is because they're in orbit around the sun. The sun is a gravitational force on them as well. So it's kind of holding them in place as well as we rotate. But if we didn't have atmospheric pressure, yes, we'd die. But it also would depend on how things evolve, because most animals are designed to deal with the pressure that we live on this Earth. Maybe if someone came from outer space and didn't have the same get up we have, they'd be squashed. Or if we go to some place with not atmospheric pressure, we might blow up. All of our molecules would go out, because we need the pressure to kind of hold us together as well. That's why when people, if they come out of the spaceship, and without a pressurized suit on, they explode. That's it. They go in 10,000 million little pieces. That makes sense?
Yeah, so is that kind of what would happen to planets then if there was no pressure on them?
The planet itself, no. But the inhabitants of the planet, yes.
All right.
Yeah. And I have this 12 by 12 square. It's called a pressure mat. And I'll try to do it over here. Let's see. Yeah, I'll do it right here. So this pressure mat, if we've got 14.7 pounds per square inch. So it's 12 by 12, so it's 144 square inches, right? So 14 times, or 14.7 times 144 is what? A lot. What is it? Yeah, times. So we get about 2,000 pounds of atmospheric pressure sitting on this mat. Now, if I pull too hard, you see how it's coming up like that? The geniuses used a wooden knob with a metal screw. So if you pull too hard, you strip it out. And I'm pulling, but it's going to rip the thing. You want to try it? Don't pull terribly. Just pull like, don't like yank. Just. You're looking at me like I was just doing like the Weather Channel people. Oh, storm, and you see people walking behind them. No, I mean this is, you've got 2,000 pounds of pressure on this thing. If I get a little air behind it, it'll pop up. And what happens is I get a little air under it from this knob. But anyway, kind of cool. And then, in this Griffin, is probably like what would happen to us. So if I have this Coke can here, and I'm going to put a little water in it because I want to use the water to force out the air that's in this can. So let me put that can on there. I'm gonna get some ice cubes for a second. I'll be right back. So I'm going to allow the water to boil, and the steam will push all the air out and make a vacuum or a void. It'll make a void in the can. You gotta remember, atmospheric pressure wants everything to be in equilibrium. It wants to be in every space, every crevice, every hole. It wants to be everywhere. And if it can't get in, it's going to put force on that object trying to get in if there is an empty space somewhere. So right now, we're making an empty space in this can by pushing all the air out. You're like, well, there's steam in there. Yeah, there is steam in there. So steam is helping with the pressure right now. But what if I got rid of the steam very quickly? What if I cooled it down like that? What would happen? I don't see enough steam coming. We'll see. Let me get these guys out of the way. Oh. Let me put this. Okay. So I'm going to put it up here so you can see it. I see a lot of steam coming out, which means more than likely all the air is out of this can. Can you see okay, Trent? It's kind of heavy to move. So I take this, I go. This is what would happen to us if we didn't have pressurized bodies and fluids like we do. We'd be crushed like this old can. Splat. Does that make sense?
Yeah.
Yep. It's pretty, oh, darn, you saw it right there.
Yeah.
Ruined the surprise. But anyway, so that is atmospheric pressure. You can crush almost anything. We used to have, when I was taught it in Cincinnati Public, they get us these 55-gallon cans, the big like oil cans, the big tall ones, and we'd actually heat up water in it, same way, and we would then seal it off with a screw top, and we'd sit there and just watch this can just be smashed to almost nothing until it finally cracked. Then once it cracked, then the atmospheric pressure could get in that way. But you'd watch this big 55-gallon drum just, it was the most crazy sound. Like, you're like, wow, so crazy.
Why don't we do that?
I don't have a 55-gallon drum. Yeah, I guess they used to have it for some of the stuff they did. Maybe the boiler rooms or whatever. Okay, to kind of show it to you, kind of slow motion way. So, little glass here. I put a little bit of water in it. Once again, I'm going to use water to try to get rid of all of the air that's in there. Push that air out. Oh, I wonder why I kept turning the lights off for. I'm like, why did you turn the lights off? Dumb Meg. Okay. Make sure as much of the water comes out as it can. That's more effective that way.
Are you going to explode it?
I am. Just going to throw it and close it up and let it go. Just kidding.
I mean, I wouldn't be surprised.
Yeah, it may happen. I may not mean for it to happen, but it may happen. I've cracked many of these things. Look at the bottom of that thing. Okay. All the air out. Come on. Problem is, it goes up and hits there and condenses and comes back down. So let's just do this. We'll see what happens. I'm gonna put the balloon on. Okay. Let's let some of the steam fill the balloon a little bit. I have an idea. Okay. Then we're gonna sit down here and let it cool. As it cools, the water vapor is going to go back into condensed water. So it's going to create a void. Because all of a sudden it's going to go back to water, and the steam is what's keeping everything equal. So if there's no steam in there, atmospheric pressure is going to want to get into that flask. I can help it a tad bit if I don't crack it. There you go. Just cool it down a little bit quicker. This is all atmospheric pressure at work. I'm just going to step on that part. I helped that. Only because it will. Oh, that's how it gets in there. Creepy crawler.
Can we do the thing with the egg?
Whew. I could. I just don't have an egg. I have them all at home. I always keep hard-boiled eggs at home. And I've gotten to the point where it can fill up the entire flask, but I don't know if it'll do that today or not.
Cool it down.
It depends on the pressure of like the atmosphere today.
It actually depends how much air I actually got out of it. And it has something to do with the atmospheric pressure today. Pressure is very high though today. So we're not supposed to get that rain like we were supposed to get, not until like Thursday now. So which means I really should have watered my plants like yesterday. So I was like, oh, it's gonna rain tomorrow. Okay. But we're gonna let this sit there for a few minutes and see what it does. It looks like it's still growing. Growing, growing, growing. Have fun. I know. Okay, this may be pushing a little bit, but let's try it. I'll be on camera if I want to shadow something. Let's speed it up a little bit. It didn't crack. Yay.
Yeah.
Yes.
Say that now.
Come on, keep growing. But it's just so cool to think that, it's being pushed in by some unseeable force. It's just so weird. In fact, that when you drink through a straw, you're not sucking that liquid up. It's being pushed up by atmospheric pressure. When you create a vacuum, and atmospheric pressure pushes on your soda, and it goes up your straw. As soon as you stop one, it stops being pushed up. Okay. What?
I like lunch, they have like little juice cups, and you have to poke 2 holes in it to get it out.
Yeah, exactly. That's exactly it. That's exactly it. So we'll see if it gets any bigger in there. I may not have gotten all the air out, but anyway, it's kind of cool. Humpty Dumpty was pushed. Things aren't sucked. It's all relative. Okay, doke? You good?
What's happening there?
Well, I'll show you in a minute. Whoop, I forgot my little creature. Come with me, little guy.
I'm gonna pull this one.
Okay, back we go. That's just always a theory. The Humpty Dumpty was pushed, he didn't fall. Humpty Dumpty sat on a wall. Humpty Dumpty had a great fall. He didn't fall, he was pushed. It's a conspiracy theory. Try. Not real hard though. Yeah. When you pull it up, when you pull too hard, you get air where the thing's screwed in. Yeah. It's a bad design. It's a very bad design. But it makes a good point. It makes you can at least try it. Okay, so vapor pressure and boiling point. You need to know the difference between these two. And just the mere fact that vapor pressure is the pressure of the gas molecules above the surface of a liquid. Vapor pressure sits on top of liquids. Okay? And the boiling point, or boiling, is when the gas bubbles, it goes from a liquid to a gas, and they equal the vapor pressure that is pushing down on them. Then they eventually overcome it, and then you get steam. Okay? So when those little bubbles inside of the liquid have the same pressure as that of the vapor pressure, that's your boiling point. But then boiling itself is when it overcomes vapor pressure. Because it has to overcome vapor pressure in order to boil away, so to speak. Vaporize. Okay? So if you look at this again, here's evaporation. Evaporation, the water molecules overcome vapor pressure just over time. When you boil, you have this water, basically the bubbles are coming up and heat is speeding things up, so to speak, okay, and it overcomes atmospheric pressure. Again, a couple of slides to kind of show you. What the coolest part about this is this. The boiling points of water depend on the vapor pressure. It depends on the atmospheric pressure. If you're up on Mount Everest and you want to cook something, boil something, your water boils at 70 degrees Celsius. At 70 degrees, which is, it's not cooking it, it's just soaking it and making it into mush. Water is not warm, it's warm, but it's not boiling at 70 degrees Celsius. But because there's so little pressure sitting on top of the liquid, the water can boil away at a lower temperature. We were in Beaver Creek for spring break, and we were making spaghetti. Anything I learned from my past experiences. But, you know, water boiled at about 90 degrees. And so our spaghetti was a little al dente because, you know, we couldn't really boil it well enough. It just, you know, we used a microwave a couple of times to boil things. That will boil because it changes a little bit. But I mean, not terribly, but I guess because it's enclosed a little bit. But anyway, but things boil much lower temperatures depending on your altitude because the atmospheric pressure changes. If you go to sea level, it's at 100, what we expect. If you go below sea level, like maybe down in New Orleans or something, it goes up to about 100.4, a little bit above boiling. If you go down to like an underwater cavern under the ocean or something, you can actually, I mean, who does this? You know, but then it would go to about 180 degrees. So the more pressure is on top of it, the harder it is to boil. That makes sense? Yes, sir.
Is that why, like, underwater volcanoes can't, like, boil the water away?
No, I just don't know if they, it just couldn't come, it still brings some of the, comes up with steam. It still boils the water away. There's just so much water. That's what it is. I mean, no, it's, so like when if you've ever seen the bottom of the Hawaiian Islands, you know, where lava's coming up in the water, it just kind of freezes it instantaneously. It's just constantly freezing that lava. So, and then steam comes up, so. But, okay, gas laws. Now we're going to go into the gas laws. Gas laws look at 4 different things. They look at pressure, volume, temperature, and number of moles. This is number of moles. Volume must be in liters. Temperature must be in Kelvin. Pressure can be in atmospheres, kilopascals, torrs, millimeters of mercury. It can be in any of those. But you have to have volume in liters, and temperature has to be in Kelvin.
What's the instant?
Number of moles. Okay? So, start with Boyle's law. Boyle's law shows the relationship between pressure and volume, where temperature doesn't change and the number of moles does not change. Okay? It has everything to do with pressure and volume. They are inversely related. What's inversely related mean?
One goes down, the other goes up.
Good. One goes down, the other goes up. For example, if you look back here. There you go. Okay. Bring him with me again. So if you look back here, over here this time. This is a glass bell jar, and I blew up a balloon about this big. I put a little bit of air in it, and I hung it from the top of this bell jar. The temperature has been the same all day, about 70 degrees in here, and the number of moles hasn't changed. That's the exact same amount I put in this morning. Okay? I can't do much else, but I can reduce the pressure. I can take air out of this bell jar and reduce the pressure that's on the balloon. So if the pressure goes down, what should the balloon do?
Expand.
It should expand. Good choice of words. I'm doing absolutely nothing to it except for taking away pressure. So because there's no pressure on it, it can get as big as it wants. So then get all the air out. But will you hear anything if it pops? You scream in a vacuum. Will anyone hear you?
Is it gonna pop?
I don't know. I've not let it get this big with the other groups because I didn't want to have to keep putting new balloons in there. So if you guys, I'll just let you, we'll see. The suspense is killing me.
Go until it's low.
It's a 12-inch balloon, so. But it looks like, I don't think any more air is coming out of it. No, unfortunately, no. Okay. So that's as big as I could get it. So, and it'll stay like that as long as the pressure is decreased.
Why would it keep going?
This thing wasn't pulling more air out. So. But then if I let the pressure back in, the balloon will go right back to the same size it was when it started. Air is being pushed into the glass jar. Wow. Okay, now one other thing. So now we'll try something else. Oh my gosh, come up here. Oh, there it goes. Okay, now let's have some fun. You know when you buy shaving cream, it is, I know, wait till it's about 90% air. All it is. Someone put this under here for me when I pick this guy up. Oh, there we go. This is it. Thank you. So you buy lots. That's why I buy the gel stuff. I don't buy the. I like shaving cream, but it's all air, so I buy like the gel stuff now. Get them more for your money. Okay. So let's. Air is trapped in that foam. Letting it, the foam's like, yes, I'm not contained anymore. Oh, I forgot the balloon was there still. We got a double whammy. I don't know. Oh, carnage! Okay. I do want to stop it there because I do not want to get pulled into the vacuum pump. Okay? Wow. That's kind of fun, isn't it? I completely forgot about the balloon being there. How silly of me. But then, we let the air back in. Ready?
Oh, I thought it was all going to go back in the car.
No. But if you look at anyway, look what you bought. That's all the shaving cream you had. It looked like you had so much more. But look, it's not. It's just a little bit. Because it was all pumped full of air. Just like a marshmallow.
Wait, did you empty out the whole can?
No, I filled up.
What do you put the can in there?
What do you think's going to happen? No, I cannot try it. 9 little ones. So, but this is all that's left. I filled it almost all the way up, and that is definitely not a beaker full of shaving cream. Okay? So, oops, let me go down there. Yeah. Anyway, so Boyle's Law is kind of fun, you know. It shows you a relationship between volume and pressure. But they are directly proportional. The dope. Come with me, little guy. Back up, here we go. Have robot will travel. Okay. So, Mr. Boyle. So Boyle's Law is, Boyle's P1 V1 equals P2 V2. We're looking at the pressure before and the volume before and the pressure after and the volume after. We're seeing what kind of changes happened. I don't care about that. Don't worry about that. So there is the formula. And remember, temperature and the number of moles are constant. They did not change. Back there, the temperature didn't change. The number of moles didn't change. I just changed the pressure. And then the volume changed accordingly. Okay? So it says, what is the new volume? So I write, what is the new volume? If a 8-liter sample, so volume 1 is 8 liters, with a pressure of 550 millimeters of mercury, changes to 2200 millimeters of mercury. So what will my new volume be? We'll kind of predict first. My volume, it starts off with 8. My pressure goes from 550 up to 220, or 2200. So my pressure is increasing. What should my volume do? Decrease. When one goes up, the other goes down. Okay, they're inversely proportional. So we say, okay, so 8 times 550 equals 2200 times x. How do I solve for that?
Divide by 2200.
I gotta multiply first. So I multiply 8 times 550.
Giving you 4,400.
4,400 equals 2200x. Then I do what, Sean?
Divide by 22.
Then I divide by 2200. So x equals 2. So it did go down. So when this decreased by or increased by a power of 4, this will decrease by the power of 4. Does that make sense? Yes? So you can kind of predict what's going to happen. You may not have numbers, but you can predict and say, okay, if I do this, this is what's going to happen with it. Okay? and Boyle's law animation. There's Boyle's law again. And Boyle's law in breathing, you know, when your diaphragm goes down, air rushes in. You do not suck in air. You do not breathe in. You might breathe in, but when you go, it rushes in your mouth. I mean, or your nose. And try holding your nose and close your mouth and try to get your diaphragm to go down. You can't. Okay? I mean, you can, but no air comes in because you closed off the path for it to come in. Or, you know, you try to, I guess you can't, like, I don't know. Yeah.
When you like close your eyes, you close your nose and your mouth, and you like breathe up. Why are your ears pop?
Because all this is connected to your sinuses and your ears. So when you go like that, whew, that was a little crazy. It just changes the pressure in your ears. Oh, that's really embarrassing. It's like got a picture of my gut. Turn. I'll stand like this now, I think. But anyway, so Boyle's law helps explain breathing. Because you breathe in, air rushes in, your diaphragm goes back up and pushes all the air out. Like that. Okay? Makes sense? But it was funny when it was on TV, on the movie, I walked around, I saw y'all going, it was like you were really paying attention to your breathing. It was so funny. Okay, so, I should pause this thing. How can I pause it? 9.